Namaskara. We have been discussing about a divide and conquer algorithm for finding min and max in an array of n numbers. The naive algorithm, which is a divide and conquer algorithm, which splits all the way up to the smallest subproblem size of 1, okay, and a complexity divide and conquer algorithm 1 had complexity 2n minus 2 comparisons, which is same as the naive 2-pass algorithm. We have seen a divide and conquer algorithm 2 that has a complexity, worst case complexity less than or equal to 5n by 3 minus 2, a saving of n by 3 comparisons, which is about 16%, 1/6. Okay. We have reduced the complexity. What we did there was we bottomed out at a larger subproblem. The algorithm 1, the recurrence equation which is analyzing the algorithm 1 had T of n equals T of floor n by 2 plus T of seal n by 2 plus 2 if n is greater than 1 and equal to 0 if n equal to 1. And this had a complexity of 2n minus 2 for all n greater than or equal to 1. Algorithm 2 had T of n is T of floor n by 2 plus T of seal n by 2 plus 2 when n is greater than 2 and this is equal to 1 when n equal to 2 and this is 0 when n equal to 1. It is a slightly different recurrence equation, but its analysis required a lot of heavy duty machineries from mathematics, and finally we got exact solution as well as upper bound. Okay. In variety of ways we provided the solution, and what we have shown in this case is that T of n is less than or equal to 5n by 3 minus 2. Okay. So, let me, did I write properly? Saving of n by 3, right. 5n by 3. Okay. Now, we are going to improve this further by looking into a clever way to split. Currently, we have split like this. N is split as floor n by 2 plus seal n by 2. We have split like this, nearly equal split. This nearly equal split may not be always a good way to split. So, when you take a closer look at the way in which the algorithms that are based on nearly equal split work, we will understand what could be a better way to split. So, we are going to take a closer look at the recursion tree, the way in which the recursion work. So, we can represent a recursion tree based on algorithm 1 and algorithm 2 and make certain observations. Okay. So, let us look at an example of 12 12 is split into 6 and 6 according to this formula, lower integral part, and 6 will be split into 3 and 3, 3 and 3, and 3 will be split into 1 and 2, 2 will be split into 1 and 1. So, in this way you are going to have 1, 2 split into 1 and 1, again 1, because we are bottoming out at 1 until you get a subproblem of size 1, you keep calling the recursion, you keep splitting the node, and you will reach the final leaf level. At leaf level, the recursion terminates and you are applying the base case, and after applying the base case you would return the value. The base case will use 0 comparison, because when you have only one item it will have 0 comparisons. No comparison is done at the leaf level. When you start with n, there will be n leaves. We have started with 12, you keep splitting until you get subproblem of size 1. Therefore, there will be 12 leaves. Because this is a full binary tree, that means every node has got 2 children or no children, right? You split or you terminate. So, it has either 2 children or 0 children. Such trees are called full binary trees. The full binary trees have a property that if you have n leaves, you will have n minus 1 internal nodes. So, you will have n minus 1 internal nodes. In each internal node, what computation is done? It receives the min and max of the left half and min and max of the right half, and min and max are computed for that particular node. So, recursive calls return. For example, if you look at this node, 2 comparisons are done here. The left half returns the min and max of these 3 numbers. The right recursive call returns the min and max of those 3 numbers. Now you are comparing the min with min, max with max. So, 2 more comparisons are done and the min and max of these 6 numbers are returned to the calling function. In other words, every internal node, in every internal node we are going to do 2 comparisons. Okay? Each leaf corresponds to base case and you do 0 comparisons. At internal node we do 2 comparisons. So, you have n leaves, n minus 1 internal nodes, and this is going to make n leaves will have this many comparisons, n minus 1 internal nodes will do this many comparisons on the whole to n minus 2. The reason why the first recurrence has 2n minus 2 as a solution is very well understood by looking into the recursion tree. The recursion tree very clearly suggests that you are going to have a tree with n leaves that will have n minus 1 internal nodes. At each internal node you do 2 comparison and at leaf you do no comparison. Okay? This is the first algorithm. That is the reason why the complexity is 2n minus 2. Now let us look at the second algorithm. Let us see how the recursion tree for the second algorithm works. If you take 12, it will be split into 6 and 6. 6 will be split into 3 and 3. 3 will be split as 1 and 2. 1 is a base case, 2 is also a base case. It will return values, no further recursive call will be done. For 3 you will split and you will get a problem of size 1 and 2. For problem of size 1 you directly solve, no further recursive call is made, that is a base case. Similarly for problem of size 2, again you directly solve and return the value. Therefore 2 is not going to have any further children. Similarly this is going to be 1 and 2, 1 and 2, 1 and 2. Note that now you have leaves, but you do not have n leaves. Here you do not have 12 leaves. In this example you have only 8 leaves, okay, you have only 8 leaves. But the cost at each leaf, if it is 1 it is 0, because if you look into the base case, if the size of the problem is 1 you return those values, but if it is 2 you do one comparison. So certain leaves you do certain comparisons, 0 1 0 1 0 1. Of course internal nodes you do only 2 comparisons, okay. In all internal nodes you do 2 comparisons, but at the leaves, if it is a leaf with weight 1 you do 0 comparison. If it is a leaf with weight 2, because if you have encountered a subproblem of size 2 you do one comparison and then return the value. So the leaves now will have mix of costs, some of them will have 0, some of them will have 1, okay. And in this way you are going to have the cost of the leaves. Internal nodes are true, but how many leaves are there and how many internal nodes are there? We do not have, earlier it was clearly n, now it is a mix of 1 and 2s. It all depends on how many 1s are there and how many 2s are there. Depending on that you will have the number of leaves. So let us assume that for a general n you have a leaves each with weight 1, b leaves with weight 2, okay. So you have started with n and then you kept splitting it and you got a leaves 1. So in this example there are 4 leaves with weight 1, there are 4 leaves with weight 2. In this example 12 when you split, finally you have 4 leaves with weight 1 and 4 leaves with weight 2. So let us assume that you have A leaves with weight 1 and B leaves with weight 2, okay. Because of this you have totally A plus B leaves, and this implies you have A plus B minus 1 internal nodes. The number of internal nodes is 1 less than number of leaves. This is a property of full binary tree, okay. For any full binary tree the relation between number of leaves and number of internal nodes is that number of internal nodes will be 1 less than number of leaves. So you have A plus B leaves means there are A plus B minus 1 internal nodes. Now what is the total cost? The total cost is at each internal node you are going to do 2 comparisons. So total number of comparisons is given by 2 times a plus b minus 1. This is at the internal node. At leaf, a leaves have, so for example these are all the leaves with weight 1, they have 0. So plus a times 0 plus b times 1. There are b leaves each with weight 2. Each with weight 2 means they will contribute to the complexity 1 because you do one comparison with this. So at leaf level b comparisons will be done. At internal node 2 times a plus this is equal to 2a plus 3b, 2a plus 3b minus 2. This is the total number of comparisons. You have a leaves with weight 1, b leaves with weight 2. That means a plus 2b is n, because it is the n that is split into. So earlier we had 12 leaves because all of them are 1, 1, 1 and 1. So 12, when you split you will have 12 leaves. Here you have split n, you have a leaves with weight 1, b leaves with weight 2. So a plus 2b is n. In this example, for instance, there are 4 with weight 1 and 4 with weight 2. So 4 plus 2 times 4, that will be 12. So you can see that we have n equal to 12. In general, n is a plus 2b. So the number of comparisons, the complexity T of n, so let us T of n is 2a plus 3b, 2a I don't know what happened, 2a plus 3b minus 2, where n equal to a plus 2b, n equal to a plus 2b. So we can express this as a function of n. Tn is 2a plus 3b minus 2 n. So if you take 2n, that will be 2a plus 4b, but here you have only 3b. Therefore I write like this, this is equal to 2a plus 4b minus b minus 2, that is equal to 2n minus b minus 2. Now you can see the advantage of our second algorithm. The advantage of the second algorithm is given or measured by b, the number of leaves with weight 2. The naive algorithm will have 2n minus 2, but this algorithm will have 2n minus b minus 2. So as many nodes with weight 2, okay, is going to give that much reduction, right. So how much our second algorithm has saved? Our second algorithm has saved b number of comparisons. What is b? Therefore b is number of leaves with weight 2. Okay. So if you look into the complexity of this method, the complexity of this method is there are 8 leaves, therefore there will be 7 internal nodes, 7 times 2 plus 4 times 1, that is 18. So the second algorithm will do 18 comparisons. The first algorithm would do 22 comparison. Why it will do 22 comparison? It is 2n minus 2, 24 minus 2, which is 22. So, how much you have saved? You have saved 4 comparisons, okay? And you can see that there are 4 nodes, 4 leaves with weight 2. That is precisely the saving, okay? So, naive algorithm, naive divide and conquer is 2n minus 2, okay? Improved divide and conquer is 2n minus 2 minus b. What is b? b is number of leaves with weight 2. We will give one more example. Okay, I will go to the next page. 17 is split into 8 and 9. 8 will be split as 4 and 4. 9 will be split as 4 and 5. 4 will be split as 2 and 2, 2 and 2, 2 and 2, 2 and 3. 3 will be split as 1 and 2. This is how it will be split. This is the tree for 17. This is the tree for 17. So, how many leaves you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 leaves. Okay? There are 9 leaves. 8 leaves have weight 2. 1 leaf has weight 1. That is the reason why you get 17. So, what will be the total cost? The total cost is for 8 leaves, 8 times 1, for 1 leaf, this is the cost at the leaf level. There are 9 leaves means there will be 8 internal nodes. The cost at internal node will be 8 times 2, which is 16. Therefore, total number of comparisons is 16 plus 8, that is equal to 24. Okay? There will be 8 internal nodes, 9 leaves. That means there are 8 internal nodes, 1, 2, 3, 4, 5, 6, 7. So, you can see this much you have saved. How much you have saved? Significant amount you have saved. Let us see how much you have saved. What is a naive algorithm? 2n minus 2, which is 2 times 17 minus 2, that is 32. The first algorithm will have complexity 32. This algorithm has complexity 24. So, you can see you have saved 8 comparison. The first algorithm would have 2n minus 2, which is 32, but this algorithm does only 24 comparisons. You have saved 8, and you can see that there are 8 leaves with weight 2. Okay? There are 8 leaves with weight 2. So, we will do little more analysis. T of n is 2n minus 2 minus b, okay, and a plus 2b is n. A plus 2b is n. We will get an idea on b. Okay, we will get an estimate on b. How many leaves with 2 possible? Okay, n by 2. All the leaf can be 2. For example, if it is 16, 16 will be split into 16 will be split into 8 and 8, 8 will be split into 4 and 4 like this, 4 will be split into 2 and 2, there will be 8 leaves. You cannot have more than n by 2. Therefore, the first thing that we get is B is less than or equal to n by 2. One upper bound we have. B is less than or equal to n by 2. We also see that A is less than or equal to B. Why A is less than or equal to B? If there is a 1, there must be a corresponding 2, because we are not splitting 2. If you are splitting 2, you will get 1 and 1. We are never splitting 2. We may split 3, in which case I will have a 1 and then I will have a 2. When you split 4, you have 2 and 2 only, there is no 1. So, what is important to observe is, if there is a 1, there is definitely a corresponding 2. Okay? So, for every leaf which has a 1, there will be a leaf with 2. But there may be leaves that may not have a corresponding, there may not have a node that has got 1 as a leaf. For example, when you split 4, it is split as 2 and 2. So, there may be more 2's than 1. That is the reason why A is less than or equal to B. A is less than or equal to B because for every leaf with weight 1, okay, its sibling will have weight 2. It will have weight 2. Why it should have weight 2? Can I have a node that has got 1 as well as its sibling 1? If this is the case, this must be 2, but we never split 2. So, 1 cannot have its sibling, 1 cannot have its sibling as 1, it must be 2. Therefore, every one will have a corresponding 2. Every leaf with weight 1 will have a corresponding leaf with weight 2, but there may be other leaves with weight 2. Therefore, the number of leaves with weight 2 is greater than or equal to number of leaves with weight 1, and that is what is written here. A is less than or equal to B. So, when you substitute A is less than or substitute B, you get B plus 2B is greater than or equal to n. I have replaced A with a larger value. So, left hand side has become larger, that is 3B is greater than or equal to n, or B is greater than or equal to n by 3. We have seen that B is less than or equal to n by 2, B is greater than or equal to n by 3. Therefore, we have n by 3 less than or equal to B less than or equal to n by 2. Okay. Now, you see T of n, it is minus B. So, replace it with a smaller value, T of n is less than or equal to we will write first equality step. T of n is equal to 2n minus 2 minus b, which is less than or equal to 2n minus 2 minus n by 3. Okay, it is cluttering here. I will go to the next page. T of n is equal to 2n minus 2 minus b, b is greater than or equal to n by 3. So, I can replace it with a smaller value and I get less than or equal to 2n minus 2 minus n by 3, because I am replacing with a smaller number. So, the right hand side becomes larger, which is equal to 5n by 3 minus 2. So, I know that b is greater than or equal to n by 3. That is the reason why the second algorithm's upper bound is 5n by 3 minus 3. Now, you can see how this recursion tree is so helpful, gives so much insight. Okay. So, whenever I split into two parts and when I get to the leaf level, okay, it may have 1 and 2, a combination of 1 and 2. When I have that kind of a combination of 1 and 2, I will have b greater than or equal to n by 3. But you know that n by 3 is less than or equal to b less than or equal to n by 2. So, if you want maximum mileage out of this idea, you have to maximize b. So, b can be maximum n by 2, b can be maximum n by 2. So, can I have a splitting mechanism in which I will have b to be n by 2? Is it possible to have n by 2 b's? If that is the case, then I will subtract n by 2 from this. In other words, maximum gain I get. The number of comparisons I am reducing is b, and b is the number of leaves with 2. So, how do I maximize the number of leaves which have got 2 in them? So, the idea is an even number should be split as even number. An even number should be split as an even number. Then that smaller even number will be further split into an even number, and in this way it will be split only as 2's and combination of 2's. Okay? So, let me write the strategy. How to maximize b? How to maximize b? Split an even number into smaller even number. Into a smaller even number. This is not done by floor n by 2, seal n by 2. What happens is, when you split n as floor n by 2 and seal n by 2, sometimes an even number may be split into odd number. That is the case for 6. 6 is split into 3 and 3. Such a split brings more odd numbers. But split this into 2 and 4. Do not split 6 as 3 and 3, split as 2 and 4. So, an even number must be split into even number, an odd number has to be split as even and odd. There is no doubt about it. Okay. So, an odd number is split as even and odd, but I want an even numbers to be split only like this. How do you mathematically say this? There are two kinds of even numbers when you divide by 4. So 4n is a multiple of 4, or it is of the form 4n plus 2. 4n will be split as 2n and 2n. This is even, both of them are even. But 4n plus 2, when you split equally, it splits into 2n plus 1 and 2n plus 1. I do not want this split. I want to split this as 2n and 2n plus 2, so that both are even. The other case is simple, 4n plus 1, 4n plus 3. This you split n by 2, floor n by 2 and seal n by 2. So this will split as 2n and 2n plus 1. It will split as 2n plus 1 and 2n plus 2. One of them will be odd, another will be even. That is okay. Odd number you can't do anything. But the even number must be split like this. When you split an even number like this, you are going to have maximum number of 2's. Let us look at 12. 12 is 6 and 6. Now 6 is not going to be split as 3 and 3. It will be split as 2 and 4. This will be split as 2 and 4. 4 will be split as 2 and 2. This 4 will be split as 2 and 2. Now you see that it is a much smaller tree, much smaller tree. Let us say n is even. If n is even, if n is even, it will have n by 2 leaves. It will have n by 2 leaves, each weight 2. So it will have n by 2 minus 1 internal nodes. It will have n by 2 minus 1 internal nodes. What will be the total number of comparisons? Number of comparisons will be 2 times n by 2 minus 1 plus n by 2 leaves each with cost 1, that is 3n by 2 minus 2. This is same as 2n minus 2 minus n by 2. This is B. What is B here? B is n by 2, number of leaves with. So you get 3n by 2 minus 2 algorithm. We can argue for n equal to odd in the same way. We will see the detail in our next session.